All right, let's continue our a concept of aligned angles and see where it takes us. In the last video, as a quick refresher, if you remember, I introduced you to the concept of complementary angles and what are cofunctions and stuff like that. And as an example, we took this piece over here to help us understand how does the trigonometry functions behave when we bring in two angles that are complementary. In this case, we took theta and 90 minus theta, and we figured out that whenever such kind of functions come in or such kind of angles come in play, in this case theta and 90 minus theta, the concept of cofunctions kick in. The values, what does it means is the value of this function, whether it's sine theta or cos 90 minus theta, which is the complementary angle, the value and the algebraic sign remain the same in this case. But by and large, what we're trying to say is this function sine and this cosine 90 minus theta, they exhibit a relationship in a specific way, and hence they are co-functions. And if you remember, we kind of discussed this also, and there will be always a prefix, a co as a co, to determine that it's a co-function of some other function. In this case, a sine. Cosine is the co-function of sine, or sine and cosine are co-functions. Similarly, sec and cosec and tan and cotan and so on and so forth. So we discussed this last time. That was just quick setting up the stage for the next session that we're going to do today. And just kind of a note, a word of caution over here is like, remember, these are like co-functions, okay? Sine and cosine are co-functions with this kind of relationship. And they are completely different than sine and cosecant, right? Sine and cosecant here, over here, if you see, sine and cosecant are reciprocal function. What does that mean? It means if sine is opposite upon hypotenuse, and then cosec is hypotenuse opposite upon opposite. Sorry about that. So in this case, remember, these are reciprocal functions, whereas this and this, okay, let me take a different marker, hold on. So this and this are reciprocal, whereas this and this are co-functions. So always remember that. So don't get confused between the reciprocal and the co-functions, with the only exception that tan and cotan, they are both co-functions over here, and also reciprocals of each other. If you see here, tan and cotan, they are also reciprocals of each other. So if you switch the denominator and numerator, you can move into another function, and incidentally, they are also co-functions. So just kind of a side note there. All right, let's move on. So that brings us to the concept of something called as allied angles. And before defining what is allied angle, let me put some scenarios. Let's play around some of the trigonometric functions and how they exhibit a peculiar pattern, and that way it will be easier for us to dive into what is the concept of allied angles and how we can define that, because we can meaningfully derive the definition instead of putting the definition first and trying to explain that. Okay, so over here, if you see, we spoke about theta, 90 minus theta and stuff like that. So what if it's not 90 minus theta? What will happen if it's not 90 minus theta? What if it's 90 plus theta, or it's some multiple of 90 degrees, which is 180 plus theta, 180 minus theta, 270 plus theta, or 270 plus a, whatever the angle? What will happen? How will the relationship between the trigonometric functions will change, or it will change if this kind of peculiar angles come in? Or instead of giving you a relative angle where we really don't know what is the angle of this a, we just over here we just say 90 plus a. But what if someone gives you a crazy angle over here? Let's say I want to find out the value of cosine of 3660, or sine of 720, or cos of minus 780, which is typically much larger than the angles that we know over here, which is typically, let me take it here, which is typically 30, 45, 60, 90 degrees kind of thing, which is more or less a kind of a reference angle, or not a reference angle, more or less like a standard angle which have a specific definition and for which the values are very easy to remember. What if you don't get that, if you're not able to fit in those kind of formula? If you remember, when we did the type 1 problems, we were trying to ensure if the angle that was given, for example, say find the value of say sine 120. So we are just trying to break it apart into sum and difference formula. Say, okay, 120 can be broken into a 90 plus 30 or something like that, and then we were trying to apply the sum and difference formula and calculating that. But in those case, it was easy to break it into two angles, which kind of fits into the type 1 format of sum and difference angle. But what if you are given a number which is much larger, like I explained to you, so let's say sine 720, and which may not necessarily fit into that format where you can easily break it down into two standard angles less than between 0 and 90 degrees. What if you're not able to do that, and it's like a kind of obscene or like a bigger angle that it's like you need to really calculate? What will happen in that? How do you calculate the values? So allied angles kind of helps you calculate those kind of things, and some of the concepts that we learned in the previous will still apply, but there's just an extension to that, and it just gives you a better way of calculating the value of trigonometry functions or simplifying that using the concept of allied angles. So just kind of a level setting there. Okay, now let's see what are allied angles and what happens when we talk about this particular angles which are multiples of 90 degrees plus or minus. So you know that the unit circle, this always kind of, we are going to carry it forward all the way whenever we do trigonometry. So this unit circle is divided into 4 quadrants, and we know using the cast logic the values of trigonometry where sine will be positive, where cos will be positive, and so on and so forth. And these are all your standard angles, 0, 30, 45, 60, 90. And again, although the angle grows on 120, but technically it's like if this piece is still 30, and we can always apply the concept of reference angles, and we can fill in this. And if you see the pattern, if you're not already, you'll notice that the values just keep on repeating. It doesn't change. What changes is the algebraic sign. The value is always repeating based on where the function falls. So we know that. So with this in mind, it will be easier for you to help how allied angles function. So let's take the first example. The first two examples, if you see, cos of 90 minus a and sine of 90 minus a, pretty much are the same thing that we covered here. But over here, I just introduced you to the concept in the context of a reference triangle, and I just took this basic table I was trying to explain you. The same thing I want to explain you under the construct of allied angle and see how it makes sense. So let's say that I want to find out if I am finding the value of given an angle A, some value, and if I'm trying to find the value of cos of 90 minus A, and after I find the value, does it exhibit or does it have any relationship with any other function or a cofunction? Is it true? Let's find out. In this case, we know, but let's assume for a moment that you do not know. So let's find out. And just think, see here, like 90 minus A, I've just intentionally made it like 1 into 90 minus A, and I'll explain you why it is. But for the time being, just hold the thought that 90 minus A is nothing but odd. If you multiply by 1 is an odd number, so it's just a odd multiple over here that I'm introducing, and let's see what happens there. Okay, so let's say I want to find out what is 90 minus A. Let's take that. Okay, and A could be any angle that could be given, or you will have to imagine that. So let's figure out. So what I've done is, for the sake of simplicity, this is our unit circle, and I've assumed 4 possible values of A, each angle falling in one quadrant. So I'm taking angle A 30 degrees, which falls in quadrant 1. Then I'm taking 120, and then I'm taking 210, and then I'm taking I think 300, right, over here. So I've intentionally taken one angle in each quadrant to see if whatever I'm saying, whatever we are trying to derive, is it true for all cases. Okay, and let's go to the next step. So let's say that the given angle is one of this, either it's 30, 120, 210 or 300, and I'm just trying to find out what is cos 90 minus a here, right? Cos 90 minus a. This is what I mentioned here. So 90 minus a is whatever I put in this yellow box. So 90 minus 30, 90 minus 120, 90 minus 210, 90 minus 300. So I've just written the equation just for ease of readability. And then I'm just doing the simple subtraction. 90 minus 30 is 60. 90 minus 120 is minus 30 and stuff like that. And we know that in the case of cos, even if you're going to introduce a negative function, cos being an even function that we have learned over here, cos of minus a, the negative sign does not have any impact. You can just ignore it and you can just compute the value of cos and the equation will be true. So in this case, cos of negative 30 becomes cos of 30. In this case, cos of minus 120 becomes 120 and negative 210 becomes 210. So that we have learned. So I just did the simple maths. So now we have the given angles in this yellow and we have computed what the angle that will be formed after we subtract 90 minus that angle, and this is over here, right? Okay, so now, and for ease of thing, I've also put the quadrant. And remember one thing, whenever you add the quadrant, for the time being, you always compute the quadrant of the given angle. What does that mean? So the given angle is 30. So don't take that, sorry. You take the angle of the bigger angle, whatever is the function that you're trying to calculate, 90 plus, 90 minus, whatever that is, okay? So in this case, what will happen is, so 90 minus 30. So if you take 90 here, 90 is over here, right? 90 is here. Let me take a different color, it will be easy for you. So 90 is this yellow bar. Okay, let's see. Okay, so once again, it's not coloring up. Okay, anyway, 90 is this y-axis, right? So 90 minus 30. Whenever you say minus, you are moving the angle in the clockwise direction. This is 90, and if I'm moving in the clockwise direction, this is the way I'm moving, right? So 90 minus 30 will be cos 60, and 60 degrees is always in the first quadrant, so I've written the first quadrant, and so on and so forth. So if in this case 90 minus 120, so I'm 90 is on the y-axis. From here clockwise I need to move 120 degrees over here, right? 120 will fall into the next quadrant, which is quadrant 4. Alternatively, you can calculate from here also. It's cos of minus 30. You know that minus 30 means you have to rotate clockwise. So from a 0 degrees, you rotate 30 degrees. So it falls in the fourth quadrant. And hence, I know cos of a function. Based on these quadrants, I would be able to apply the cast logic, CAST, and figure out the formula. So I know that cos is always going to be positive in quadrant 1 and quadrant 4, and hence I've written positive and positive here. And cos is going to be negative in quadrant 3 and quadrant 2, I've written negative, negative. And that's the reason I took one angle from each quadrant so that you know the spread, how the values are coming. And moving on, so we know that cos of 60 from here, cos of 60, we know the value of the cos function is nothing but the value of the x coordinate. Over here it's half, so we have taken half here. Cos of 30 here, or cos of, even if you're taking minus 30, just to make sure there is a minus sign here, the value of cos function of cos of 30 is the x coordinate, which is root 3 by 2, and so on and so forth. So we have the green bar here, right? It shows over here, it shows that we have computed the value of cos 90 minus a. Okay, so we have got all these values, we have got the 4 values. Now let's see if it has any relationship with any of the other function. So let's take the given angle a. Okay, this is the given angle a, so don't forget that. So one is the given angle a and other is the 90 minus a. So we computed so far the 90 minus a, and the algebraic sign will be always for the bigger angle, right, wherever you're doing the bigger maths. So now let's see, if you take the given angle a, which is this yellow bar, let's compute the value of sine of a, sine of this, all of this yellow bar. So we get sine of 30, we get sine of 120, we get sine of 210, and we get sine of 300, and we are computing the values, right? We know that. So with this orange bar here and with this green bar here, the values that we get here, one second, let me circle it up, over here and over here. all right, over here and over here, and similarly over here, over here, and over here, and over here. If you see these values here, they not only match in the numerical sign, they also match perfectly with the algebraic sign. So wherever there is positive, there is positive. Wherever there is negative, right, over here. So that means we can safely conclude what we spoke here from a conceptual standpoint. We have kind of proved with this logic that cos of 90 minus a, cos of 90 minus a that we calculated over here is equal to sine of a, because a and 90 minus a are anyway complementary angles, and we're just trying to reiterate the same thing, that cos 90 minus a will be equal to sine of a, and both of them match in numerical value and also in the algebraic sign, right? So we got one definition. So what did we learn here? Whenever we are moving around the 90 degrees or the y-axis, 90 degrees is on the y-axis, or we are taking an odd multiple of 90, it's all the same, and 90 minus a is nothing but a clockwise movement. So whenever we do that, we get this equation. We have proved that. Similarly, I'm not going to explain you that. In a similar concept, sine of 90 minus a also exhibits a relationship the same way, which is given here. The sine of 90 minus a has a relationship with the cos. Sine and cosine in this case are cofunctions. Here also we saw that if whenever there's 90 minus a involved, the cofunctions kick in. Like we have cos here, you get sine here. In this case, you get sine here, you get cosine here. So the cofunctions come into play. Let's move on. Now let's say instead of 90 minus a, let's say we are talking about 90 plus a. And what does it mean? It means the same thing, but you're moving in the opposite direction. So this is your 90 degrees, right? This, if you say pi by 2, this is your 90 degrees. And if you say plus a is a given angle, right? Any angle. And we have just taken examples over here, 30, 120, 210, 300. That pretty much I'm keeping constant all over the table, so that will be easy. So for any given angle a, if you want to compute cos of 90 plus a, that means 90 is here. And when I say plus, I'm going to move into this direction, right? Anti-clockwise. Okay, and based on that, if I apply the cast logic, I'll be knowing the quadrant, and from the quadrant I can determine the sine. That's what it says. For example, sine, now cosine of 90 plus a is 30, 90 plus 30 is 120, and I know that cos 120 lies in quadrant 2. That's why I've written quadrant 2, and I also know that based on the cast logic, in quadrant 2 cos will be always negative, right? And so on and so forth. So I determine this particular piece that you guys know, and then I get the value of 90 minus a, whatever that is. So for example, cos of 120 is minus half. If you see cos of 120, here is the x coordinate, it's minus half. If you take cos of say 300, 300 is over here, right? 300 is over here. If you take the x coordinate, 300 is over here, 300 is over here. If you take the x coordinate, it's plus half, right? Plus half over here. So let's see if this function has a relationship with any other function. And we have taken sine function here. So if we take the sine of the given angle, all of this, I've computed the value. Okay, so this orange bar over here is all the sine functions. So if you see the green bar and the orange bar, you will notice that the numerical values are the same, right? And the algebraic signs are opposite. If you have negative here, it is positive here. If it's negative and positive, if it's positive here in the green bar, the orange bar is negative. So you can see that. So in that way, we can conclude that whenever you're moving clockwise, anti-clockwise, or whenever you're adding the angle 90 plus a, in this case, what happens is the cosine function still has a relationship with this, its cofunction, which is sine, but the algebraic sign kind of changes here. It's opposite. Whereas in the previous example, it was same for the numerical value as well as the algebraic sign. Whereas in this case, it's the numerical value matches, but the algebraic sign is kind of opposite. Okay, so that's kind of this thing, and I'll come to a point where I'm going with this and how to remember this. So all you have to remember is the algebraic sign always is derived from the bigger angle, right? Take the bigger angle and find the quadrant, and whatever quadrant is that, the final answer will always retain that algebraic equation. Don't get confused with the algebraic angle of algebraic sign of this function, the smaller function, and just go with the bigger function, and whatever is the algebraic sign, just retain that in the final formula. So just hold the thought for now, and I'll come how to apply that while remembering these functions. And again, 90 plus a is nothing but an odd multiple of 90, and whenever I say 90, it's around the y-axis, right? So just remember that you have clockwise movement if you do plus, which is plus a. In the previous example it was minus a, you had the anti-clockwise movement, right? Simple. So moving on, so on and so forth, we have derived sine of 90 plus a also, and we have proved that sine of 90 plus a also has a relationship with this cofunction, and in this case not only the numerical value matches, even the algebraic value matches. So in this case there is no play of algebraic sign, you just match the numeric and algebraic sign both, so it's straightforward. So till now we have seen the formulas for the 90 plus a, or the odd multiple of 90s, or the angles relative to the y-axis, whether clockwise or anti-clockwise. Now let's take a different example by taking 180 degrees. In other words, let's take an even multiple of 90. 180 is nothing but an even multiple of 92 into 90. Other words, what happens if the angle rotates along the x-axis, whether it's 180 or 160, it's all multiple of even multiples of 90. So in the previous case, we were talking about clockwise or anti-clockwise movement along the y-axis or 90 degrees. In this case, let's talk about clockwise or anti-clockwise movements along the x-axis, or 180 degrees or 360 degrees, just an even multiple. It's all the same. So the way we put up, whether we call along x-axis, or we say even multiple of 90, or we say 180, or we say 360, all mean the same. Similarly, when we say odd multiple of 90, when we say pi by 2, when we say y-axis, it all means the same. Okay, just keep that in mind. So they're only odd and even multiples. That way it will be very easy for you. So in this case, if you see what happens if I have to find the value of cos 180 minus a, in other words, if I have to find the value of an even multiple of an angle, 180 is 2 into 90, and again let's say we have taken a given angle 30, 120, 210 and 300. What happens? Is there a pattern of the same relationship or something changes? Let's find it out. And we do the maths here. Like I said, I'm just taking 180 minus a, I put everything here, I'm computing, I'm calculating the quadrant, which is more important because 150 is here, it's in quadrant 2. In quadrant 2, I know that cosine function is going to be negative, and the value of that is x coordinate minus 3 by 2, root 3 by 2, and so on and so forth. So that way I fill up this green bar, I know that. Okay, now let's see what is the relationship of this with another function. So if you see over here in the green bar, I have found out the value of cos 180 minus a, which means 180 is here, and when I say minus a, I'm going to move clockwise. So this is the direction, right? That's the direction along the x-axis. I'm going to move clockwise. So I found out this green bar is all those values in the clockwise direction along the x-axis with reference to the x-axis. And if you see the values here, what you will notice is for the given angle, in the previous functions we did a sine, we took the sine value, right, cofunction. But over here, whenever I do 180 or whenever I do a even multiple of 90 degrees, or I rotate the angle along the x-axis, the cofunction does not come in play. But what happens is the value of the bigger angle is the same as the value of the same function, not the cofunction. What does it mean? So cosine of 180 minus a is equal to a, because if you see here negative a, for example, if you see here this orange bar, I've taken the values of cosine of all the functions that you've given, 30, 120, 210 and 300. If you see the values are plotted here, right, from this unit circle we can plot. And if you see the values on the green bar and the orange bar, you will notice that They are same in terms of numerical values, but they are opposite in terms of algebraic signs, right? So, okay, so with that, we can conclude that whenever you have an angle which is either 180 or even multiple of 90, or when you're rotating the angle clockwise or anti-clockwise along the x-axis, all mean the same. The value of the trigonometry function will be equal to the value of this angle A for the same trigonometric function. So the cofunctions does not come in play. It does not come in play. So cos remains cos, sine will remain sine, tan will remain tan. So whenever the 180 degrees come in play, there is no cofunction in place. Whenever there is 90, the cofunctions come in play. The sine becomes cos and cos becomes sine, right? So that's kind of the trick here. And so on and so forth. I've calculated for a sine of 180 minus a and 180 plus a. And again, over here, we are talking about 180 plus a, which is anti-clockwise rotation and stuff like that. It's the same thing. So now what we have done in essence is we have calculated, we have established a relationship between two trigonometric functions based on whether it's odd multiple of 90 rotation or an even multiple of 90, or whether you're rotating the angle along the x-axis or you are rotating the angle along y-axis. And what did we conclude? This is what we concluded. So we concluded for odd multiples of 90, primarily rotating the angle along the y-axis, the cofunctions come in play. What does that mean? Sine becomes cosine and vice versa, that we have seen all the cofunctions come in play. And for even multiples of 90, which is 2 into 90, which is 180 degrees, pretty much anything along the x-axis, the cofunctions do not come in play. The functions remain the same. Sine remains the same, cosine remains cosine, and stuff like that. So the numerical value we already established how it will change. What about the algebraic sign? Like I told you, the trick is the algebraic sign. You always remember, take the bigger angle, whatever is the bigger angle, when you do the summation of the two angles or the difference of two angles, whatever that angle is, wherever that angle falls, in whichever quadrant it falls, you will always retain the algebraic sign of that in the final answer. So if you remember that, you can remember these formulas. Okay, let me repeat it again. The algebraic sign will be always inherited from the bigger angle when you combine those two angles, whether you add or subtract, whether you say 180 plus a or 180 minus a, 180 plus 30 or 180 minus 30. Whenever you do the maths on those two angles, whichever quadrant that angle falls in over here, right, you will always retain that algebraic sign in the final answer. So that's how you remember. So these are three simple rules. For odd multiples, cofunctions come in play. For even multiples, cofunctions do not come in play, and the algebraic sign will be the sign of the bigger angle of whatever is the function, right? So, and to put in a perspective, like for example, I've taken all the odd multiples, whether it's 90 plus a or 90 minus a, and what we are trying to say is whenever it's odd multiple, which is rotation along the y-axis, cofunctions will come in play. Sine will become cosine, cosine will become sine, and so on and so forth. Likewise, even if it's plus, since it's an odd multiple of 90, sine will move into cosine, cosine will have a cofunction of sine, and the algebraic sign over here, right, will depend upon this angles over here. Whichever quadrant these angles fall, all of this, the algebraic sign will be borrowed from that, and you can just add that this way. And if you remember, it's a simple way. So just you remember here I have taken all those four angles, right? So now you understood the concept. But when you apply what should be the algebraic sign, just take any one arbitrary angle. Take one small angle, 30 degrees. Okay. And if you say 90 plus a, I know that we're talking about 180 plus a here. So that means I'm going to rotate around the x-axis, or it's an even multiple of 180. So I know that the cofunction will not come in. The original function will be the same on the right hand side. So sine will become sine only, but I'm not sure what is the algebraic sign. And the way to remember is in your head, just take the small acute angle, and that's what the exams will ask. The exams are not going to ask you this bigger angles. They'll just ask you add any small angle, say you have to find out what is sine of 180 plus a. You know that it's along the x-axis or the rotation along 180 or even multiple of 90. In this case, sine is going to be sine, but what about the algebraic sine? The simple way is take any one small angle. 180 is here, and let's say I'm taking an angle of 30. So when I say 180 plus 30, 180 plus a, pretty much I'm going to rotate it in anti-clockwise direction, right? I'm going to if you take 180 plus a, I'm going to go into this direction. I'm going to move into anti-clockwise direction, and a is a small angle, 30 degrees. So 180 plus 30 is going to be 210, and 210 falls in quadrant 3. In quadrant 3, sine is always going to be negative. Hence, I'm going to keep this value negative in the final answer. So that's how you need to remember the sign. What will be the sign? Same way here, if you see the algebraic sign, just add a small angle in your head and plot the unit circle, and wherever you find whichever quadrant the angle falls, you just maintain the sign so that you don't have to memorize the formula. So this is a cheat sheet, and this actual formulas are written here. If you see, whenever there's odd multiple of 90 degrees, the cofunctions come in play. Whether it's plus or minus over here, and this algebraic sign will be derived by the simple logic I gave you. Imagine in your head a small angle, calculate the combined angle, see which quadrant it falls in, and wherever sign falls, wherever the bigger function falls, the algebraic sign will be written for that. If you think that sign is going to be positive in that quadrant, then you just take plus. If you think the cosine is going to be negative in that quadrant, you take minus. That's a simple logic. And I've just plotted this graph for just cheat sheet for your understanding, so that you understand how the algebraic sign comes in and how the numerical value comes in. And with that, now we can define what is an allied angle. So now we understood what is that. So whenever there are two angles, right, any two angles, 180 plus a, so 180 is one angle and a is another angle. So whenever there is in this case 180 plus a or 180 minus a, 90 plus a or 90 minus a, or 360 plus a or 360 minus a, whenever we take two angles, okay, and the sum or the difference of those two angles are either 0 or a multiple of 90, like we have seen, those kind of two angles, those two angles are called as allied, because they are ally of each other, because they exhibit a specific relationship based on what function it is. And the examples are, if you take any given angle a theta, which is a in our example, like if you see here, for any given angle a, okay, all these things are allied angles. So the same thing I put in the definition for you to remember. For any angle theta, all of this 90 plus theta, 90 minus theta, 180 plus, because if you take 90 plus theta, it will be 90. So the sum of this angle and the sum of this angle will be a multiple of 90, or it will be 0. And why 0? Because you can have two angles, 30 and minus 30, and if you add them, it becomes 0. In this case, it's a rotation around the x-axis, like I've shown you here, like here at 30 here, and minus 30 and plus 30. If you add that, it becomes 0, and you can still compute the value. And 0 is nothing but rotation along the x-axis, and it's like you can assume that it's 0 multiplied by 90. It's again not an even multiple, but it's multiplication around it's a rotation along the x-axis, and hence they have included 0 also, so that we don't forget that, right? So that's kind of the concept of allied angles, which you remember. I don't think they'll ask you the definition of allied angles, but if they ask you any two angles which have, for when you sum them up or have a difference, and the sum and difference of the angles are either 0 or multiple of 90, those are called allied angles. And this is like the very cheat sheet for the table, but you don't have to remember the table. I've told you the simple way when the cofunctions will kick in, when the cofunctions will not kick in, and how to retain the sign. So this table is plotted using that logic, so you don't have to memorize that. It's just put for your reference, compiling everything that we have learned so far, but just use the same formula. See whether it's a odd multiple of 90 or even multiple of 90. In other words, are you going to rotate around x-axis or you're going to rotate around y-axis? In other words, is it 90 or is it going to be 180? Stop. It's all the same. Calculate that and borrow the algebraic sign from the bigger angle, where you are forming the sum of the difference of the angle 90 plus a or 90 minus a. Take the algebraic sign of that and make sure that you plug it into the final answer to give you the algebraic equation of what 90 plus a or 90 minus a or 180 plus a and 180 minus a might translate. So that's all we have for today on the allied angles. Hopefully you guys got the concept, and the next session will solve some of the examples that came in the past question papers, and we can be able to easily understand that and apply it. And I promise you that it's not that difficult, and with this logic you'll be able to easily score the easy ones without having any problem. Okay, so more on the next video. Thank you guys.